Welcome to this lecture number 16 in our course on fundamentals of transport processes. In the previous lecture, we were discussing molecular diffusion, okay, and how we get the constitutive relations based upon molecular diffusion. Okay. The discussion in the previous lecture was restricted to diffusion in gases, mass diffusion in gases. Okay. I considered here a typical experimental configuration that is used for calculating the diffusion coefficient. You have two reservoirs with different kinds of gas molecules with a valve in between, and when you open the valve there is a transport of gases across this surface. For the present, we had considered that the molecular masses of the two gases are equal. That is a simplification, but it makes our discussion easier. If the molecular masses are equal, then there is no net motion across the surface. Okay. There is no net mass transfer across the surface at constant temperature and pressure. Okay. However, since there is a variation in concentration, there will be a transfer of the red molecules downwards and a transfer of the blue molecules upwards. And we had identified the cause for this transfer. Okay. If you expand out this region here, okay, you can see that for transfer across the surface, the molecules that are coming downwards are coming on an average at a distance above this surface comparable to the mean free path, okay, because these molecules travel distances comparable to the mean free path between collisions. Therefore, the molecules that are coming downwards are originating at some distance above the surface. That distance is comparable to the mean free path. The molecules that are going upwards are originating at some distance below the surface. That distance is also comparable to the mean free path. There is no net transport. Okay. The total number of molecules coming down has to be equal to the total number of molecules going up, because there is no mean fluid velocity at any of these locations. However, because the concentration of molecules of type A, okay, above the surface is different from the concentration of molecules of type B below the surface, there will be a net transport of molecules from above to below, because the total number of molecules at that surface above of A type is higher than the number of molecules at the surface below, and that is going to cause a net transport of molecules. Okay. There will be an equal and opposite transport of molecules of type B, okay, in the opposite direction, once again because the concentrations at these two locations are different. Okay. So, these are the diffusion fluxes due to the fluctuating velocities of the molecules. When I discussed convection, I had said that the convective transport of material is equal to the mean velocity, okay, the flux is equal to the mean velocity times the mass density or the concentration. In this case, for the diffusive flux, we have a similar relationship, except that it is not exactly equal, it is not the mean velocity, but rather the root mean square of the fluctuating velocity that has to be taken into account. Okay. So, it is the root mean square of the fluctuating velocity that is important in this case. Okay. So, therefore, the flux is proportional to the root mean square fluctuating velocity times the concentration at that average location, okay, where B is a constant and A is also a constant. It tells you what is the average distance above or below the surface from which these molecules originate. Okay. So, the flux downwards is equal to B times the concentration at the location above the surface times the root mean square fluctuating velocity. Flux upwards is equal to some constant times the concentration at the location below the surface times the fluctuating velocity. Net flux is the flux going upwards minus the flux going downwards. Okay. So, I had written that as this concentration at two different locations times the root mean square fluctuating velocity, the difference between these two. Okay. So, therefore, the flux was given by J is equal to J plus minus J minus, okay, which is equal to B times V RMS into C at z minus a lambda minus c at z plus a lambda. Okay. Now, each of these two we had expanded. Okay. We had written c at z minus a lambda is equal to c. I should try, this was actually at 0, z was 0 here. So, let me just remove that. Okay. Is equal to c at z is equal to 0 minus a lambda dc by dz at z is equal to 0 and similarly c at z is equal to plus a lambda is equal to c at plus etc. Okay. So, those are the two expressions. Now, I will take c at z minus a lambda minus c at z plus a lambda, and when I subtract the two, these terms will cancel out. Okay. And ultimately, you will be left with an equation for the diffusion flux, that is of the form B VRMS, okay, minus 2 a lambda dc by dz at z is equal to 0, okay, minus 2 a lambda the whole cube by 3 factorial, okay, plus additional terms, higher order terms. Okay. So, that is the expression for the flux. Note that when we make the linear approximation in the previous lecture, what we had done was to neglect this term and higher order terms, okay, in comparison to this term, okay, which we had assumed was going to be the largest term. Okay. So, we had cut off the series at this first term. Okay. When is this justified? Okay. If you look at this term here, okay, it scales as the ratio of a mean free path. Okay, mean free path is the molecular scale, and the gradient, okay, the gradient of the concentration. Okay. The gradient of the concentration is going to be equal to a difference in concentration, okay, a difference in concentration between these two locations divided by this macroscopic length scale. Okay. The gradient of the concentration is going to be the difference in concentration divided by this length scale over which there is a difference in concentration, the system size, if you will. Okay. Therefore, this term here will scale as a mean free path times a difference in concentration. Okay. So, this first term here will scale as a mean free path times the difference in concentration divided by the system size. Okay. The second term here will scale as the mean free path cubed, okay, because it is lambda cubed, times the third derivative of the concentration with respect to distance, okay, delta c by L cubed. Okay. So, obviously, this term can be neglected in comparison to the first term only for lambda by L being small compared to 1. Okay. Only in that case will this term be much smaller than this term here, okay, because this goes as lambda by L, the next term goes as lambda by L the whole cubed, the next term will go as lambda by L to the 5th power and so on. Okay. So, we can neglect the second term in comparison to the first only when the mean free path is much smaller than the distance over which there are concentration variations. Okay. Typically, there will be concentration variations in a reactor, for example, or distances comparable to the particle size, the catalyst size, or in the case of a heat exchanger, the temperature varies over a distance comparable to the diameter of the tube. So, therefore, only when the mean free path is much smaller than this length macroscopic length scale is this valid, and that is a point that I had emphasized in the last lecture as well. The continuum description is valid only when the system size is much larger than the molecular scales. In the case of gases, the molecular scale is the mean free path. In the case of liquid, the molecular scale is the particle diameter itself. Okay. So, if that condition is satisfied, then we can neglect all these higher terms in the expansion. Okay. We can neglect all these higher terms in the expansion and retain only the first term, and then we get this expression for the flux. Okay. And just by comparing that with the standard Fick's law for mass transfer, you can see that the diffusion coefficient is proportional to the mean free path times the fluctuating velocity. So, therefore, if we know what is the mean free path and what is the fluctuating velocity, we can get some estimate for the mass diffusion coefficient. So, we will next try to calculate what are the mean free path and the fluctuating velocity in gas molecules, in gases. Okay. The fluctuating velocity in gases can be written in a few different ways. Okay. Typically, half m Vrms square is equal to 3 by 2 kT for monatomic gases from the equipartition of energy, okay, which implies that Vrms is equal to root of 3 kT by m. Okay. So, this is the root mean square of the fluctuating velocity of the molecules. You can also define a mean velocity. Okay. The mean velocity of the molecules is sometimes defined as root of 8 kT by pi m. Okay. This is what is called the mean molecular speed. Okay. These two differ only by a constant that is of order 1. Okay. So, for the present purposes, we will use this definition of the root mean square fluctuating velocity. In any case, we do have these constants here in this expression, okay, and these constants will change depending upon which value of the gas velocity that one employs. In either case, we can use any one of these, okay, in order to just get an estimate of the diffusion coefficient. So, I will use the root mean square of the fluctuating velocity. How much is this velocity? Okay. For example, if we take the case of hydrogen gas, okay, at room temperature, okay, at standard temperature and pressure. Okay. What is the mass of a hydrogen molecule? Okay. We know that mass of 1 mole is equal to 2 grams, okay, and 1 mole is 6.023 into 10 power 23 molecules. Okay. Therefore, the mass of one molecule is equal to 2 into 10 power minus 3. 2 grams is 2 into 10 power minus 3 kilograms, okay, divided by 6.023 into 10 power 23. Okay. This works out to approximately 3.32 into 10 power minus 27 kilograms. Okay. Now, what is kT? Okay. kT is equal to 1.38 into 10 power minus 23. Okay. That is the Boltzmann constant in joules per Kelvin into, at room temperature, we will take it as approximately 300 Kelvin. Okay. This is approximately 4 into 10 power minus 21 joules. Okay. Using these two, we will find that Vrms is equal to square root of 4 into 10 power minus 21 divided by okay, which is approximately equal to 1200 meters per second, okay, approximately. Okay. You can see that quite easily. Okay. So, this is the root mean square velocity of the molecules in hydrogen gas. Okay. In oxygen gas, for example, this is for H2. Okay. The molecular weight of oxygen, okay, m is equal to 16 times m of oxygen is 16 into mass of hydrogen. Okay. It is 32, whereas hydrogen is 2, okay, which means that Vrms of oxygen is going to be approximately equal to 1 by 4. Okay. You have 1 over square root of mass in the denominator, 1 by 4 times Vrms of hydrogen, okay, which will be approximately 300 meters per second. Okay. Similarly, for air which contains nitrogen and oxygen, it is approximately the same, approximately 300 meters per second. Okay. Approximately 300 meters per second is also the speed of sound in air. Okay. It is 330 meters per second. So, therefore, the speed of the molecular fluctuating velocities is comparable to the speed of sound. Okay. And that is no surprise, because sound propagates through pressure waves through the air, and the maximum velocity with which those pressure waves can propagate has to be comparable to the molecular fluctuating velocities. Okay. So, the molecular fluctuating velocities Vrms for hydrogen is about 1200 meters per second, for oxygen it is about 300 meters per second. Okay. Now, what about the mean free path? Okay. How does one calculate, or rather estimate, the mean free path? Okay. The mean free path is the distance between two intermolecular collisions. Okay. So, if you consider one molecule as it is moving with a translation velocity v. Okay. Now, this molecule, it sweeps out a cylindrical volume. Okay. This molecule, it will sweep out a cylindrical volume, okay, as it moves along, okay, whose radius is equal to the molecular diameter, okay, such that if the center of some other molecule comes within this cylinder, that means that the two molecules have collided. Okay. That means the distance between these two has become, the centers of these two molecules has become less than a molecular diameter. That means that these two molecules have collided. Okay. So, it sweeps out a cylinder of volume of cross sectional radius d, okay, and okay, some length L. Okay. What is the total volume in this cylinder? Okay. Swept out, okay, is going to be equal to the cross sectional area pi d square times L. Okay. What is the number of second molecules in the cylinder? Okay. Has to be equal to the number density of the molecules times the volume of the cylinder. Okay. That is the number of second molecules in this cylinder. Okay. When the length is very small, the number of second molecules is also very small. Okay. So, the probability that a second molecule has collided is very small. Okay. As the length becomes larger and larger, you will have many such molecules in this volume. That means that this molecule has already collided. Okay. When does the molecule translate approximately one mean free path? That is when the number of second molecules in this cylinder is approximately 1. Okay. Therefore, it has translated a distance equal to one mean free path when n pi d square times lambda, okay, is approximately equal to 1. Okay. What that means is that the mean free path lambda is equal to 1 by n pi d square. Okay. So, this is just an order of magnitude estimate. Okay. I said that the number of second molecules has to be approximately 1 for the molecule to collide on average. Okay. And on that basis I got the mean free path to within a proportionality constant. Okay. You can do a more exact calculation, and if you do that you will find that the expression for spherical molecules for the mean free path is 1 by root 2 sorry I should write that as okay. Note that n is the number density of the molecules, okay, the number of molecules per unit volume. Okay. So, it is just a number per unit volume. Okay. So, therefore, if I have this expression for the mean free path, okay, I can then calculate what is the mean free path in real gases. Okay. So, I should correct myself. This. Okay. So, in order to estimate what is the mean free path, I need to know what is the number density of the molecules and the diameter of the molecules. Okay. So, once again, if we take the example of hydrogen, okay, the diameter of the hydrogen molecules is approximately 1.3 angstroms, okay, which is equal to 1.3 into 10 power minus 10 meters. Okay. What is the number density of the molecules? Okay. The number density of the molecules has to be, okay, you know that n by V is equal to P by kT, okay, from the ideal gas law. Okay. P is equal to, if you recall the ideal gas law, it is usually written as P is equal to NKT by V. Okay. N is the number of molecules, V is the volume. Okay. So, therefore, I can also write this as NKT, where small n is the number of molecules per unit volume. Okay. So, from the ideal gas law you get the number density of the molecules or the number of molecules per unit volume. Okay. So, n is equal to P by kT. Okay. Once again, at standard temperature and pressure, the pressure is 1.01 into 10 power 5, okay, pascals, that is in SI units. Atmospheric pressure is 10 power 5, okay, pascals, which is newtons per meter square. Okay. Now, what is kT? Okay. kT is the 1.38 into 10 power minus 23, okay, joules per Kelvin into 300 Kelvin. Okay. It is approximately 4 into 10 power minus 21 joules. Okay. So, this I have 4 into 10 power minus 21 joules. Okay. And if I divide these two up, I will get number density. N is approximately 2.5 into 10 power 25 molecules per meter cube. Okay. Pascal has dimensions of force per unit area or energy per unit volume. I am dividing it by an energy. So, I just get a number per unit volume of these molecules. Okay. And using that and the diameter of these hydrogen molecules, I can estimate the mean free path. Lambda is equal to 1 by ND square, okay, which is equal to 1 by root 2 pi into 2.5 into 10 power 25 into 1.37 into 10 power minus 10 the whole square. Okay. And this gives me a mean free path of approximately 5 into 10 power minus 7 meters, okay, which is approximately 0.5 micrometers. Okay. It is a half a micrometer. Okay. So, that is the mean free path in a gas, okay, and for the continuum approximation to be valid, I told you in the last lecture that the system size has to be much greater than this mean free path, which is about half a micron. Okay. So, continuum description in this case, in the case of gases, will be valid only when distances are larger than half a micron or so. Okay. Similarly, you can do the calculation for oxygen, nitrogen, air. Okay. For all of these things, the number density remains the same. Okay. The number density is exactly the same because it depends only on the pressure and the temperature. Okay. However, the molecular diameter, okay, d of O2 is approximately 3 or 3.3 angstroms. Okay. So, the molecular diameter is larger by a factor of 3 or so. Therefore, the mean free path goes as 1 over the diameter square. So, it will be smaller by a factor of approximately 10. Okay. Lambda is approximately equal to 6 into 10 power minus 8 meters. Okay. So, that is 0.06 microns, okay, for oxygen. Okay. So, now we have got the mean free path, we have got the molecular fluctuating velocity. From this we can estimate a diffusion coefficient. Okay. D is equal to some constant, okay, some constant times Vrms times lambda. Okay. We found that Vrms was approximately, for the case of oxygen, okay, so let us take DO2, 300 meters per second into 6 into 10 power minus 8 meters. Okay. If you work that out, you will get a constant into approximately 1.8 into 10 power minus 5 meters square per second. So, that is the diffusion coefficient, approximate diffusion coefficient for oxygen molecules, okay, translating in air. Okay. The diffusion coefficient for hydrogen molecules is slightly higher. Okay. Diffusion for hydrogen molecules is equal to C into 1200 meters per second into 5 into 10 power minus 7 meters. Okay. So, this will give me approximately a constant into 6 into 10 power minus 4 meters square per second. Okay. So, that is roughly the range of diffusion coefficients. For very small gas molecules, it will be about 10 power minus 4, but for most gas molecules, the diffusion coefficient is in the range of 10 power minus 5 meters square per second. Okay. So, that is the normal diffusion coefficient, and this comes from a molecular calculation of the actual mean free path and the fluctuating velocity in a molecule, in a gas. Okay. Note that we had earlier said that the diffusion coefficient goes as Vrms times the mean free path, okay, which is root of 3 kT by m is the root mean square velocity, and 1 by root 2 by n t square. Okay. So, this is the dependence. Okay. This is the dependence on the number density, the molecular diameter, and the molecular fluctuating velocity. Okay. I will continue this in the next lecture to give you a more precise idea of what these diffusion coefficients mean. Everything that I have done so far is only in gases. How does it translate into diffusion coefficients in liquids? Okay. Once that is done, then we will look at diffusivities for momentum and energy. Okay. And we will get diffusion coefficients for those as well in a similar manner in gases, in a more approximate manner in liquids, and that will give us some idea of how to treat diffusion in comparison to convection. Okay. So, I will continue with this diffusion calculation in the next lecture, go to diffusion coefficient in liquids, okay, and then we will look at mass diffusion, momentum diffusion and energy diffusion. So, we will continue this in the next lecture. Okay. I will see you then.